Hi, everybody. My name is Mia Reed, and I'll be the reporter for Group 2 for the Clapeyron experiment. So here's the Clapeyron equation. It's a derivative of pressure over derivative of temperature, which equals latent heat of vaporization over temperature times the volume of the vapor minus the volume of the liquid. More generally, the Clapeyron equation relates to the relationship between the pressure and temperature for conditions of equilibrium between two phases, as we see here with the vapor and liquid. So V volume of the vapor is much greater than volume of the liquid. So volume of liquid is negligible, and we see latent heat of vaporization over temperature times volume of the vapor. Furthermore, the ideal gas equation applies to the vapor. So here's the equation from the last slide. We use the ideal gas equation, which is P, pressure times volume equals R times temperature, where R is the universal gas constant as seen below. And then we manipulate this equation to be volume equals R times temperature over pressure. And here we get our new equation. For procedure 1 for this experiment, we take the instantaneous derivative at every point to get our values for dP over dt. The equation is a manipulated equation from the previous slide, so you can solve for latent heat of vaporization. So yeah, the derivative was taken at every point in each data set. And here are the graphs that came from this. These graphs are not very nice to look at. Taking the instantaneous derivative introduces lots of error because the derivative at each point changes constantly because we're taking so many points so quickly. And so this is not a good way to calculate the latent heat. In procedure 2, we tried to take away some of the error. And we do this by developing an equation relating pressure and temperature over the desired temperature range. So I got this equation by plotting temperature versus pressure and then plotting a trend line for the data. To make sure that this would work, I plotted it on top of the line. And it is a very close fit, with the exception of in the beginning, which is where a lot of noise is anyway. So this data the beginning data doesn't really give a lot to the experimental results. Okay, so I got this equation and then I took the derivative. I used that to calculate for dP over dt. Here's one example. This is for data 1 with beads. Here's the equation that I got from the trend line. I took a derivative and then plugged in T to solve for dP over dt. And I got those values, and then I plugged in for the latent heat of vaporization equation and got the second data set for procedure 2 that way. Here are the graphs of these. As you can see, very different from the procedure 1. These graphs seem to make sense. They aren't that smooth, but they make sense logically. For procedure 3, to filter out even more of the error, we use a functional behavior between the latent heat of vaporization, HFG, and we use that to obtain an expression relating to pressure and temperature that will accurately predict both pressure in terms of temperature and derivative of pressure over derivative of temperature, or derivative of pressure in terms of temperature as a function of temperature. So you can see from here, here's the general form of the equation that we were given in the lab manual. So HFG equals A plus BT. This is a standard line equation. We have to put this into our equation that we've been using the whole time. The dP over dt is HFG times P over RT squared. So we put A plus BT in terms of H, and then we do some algebra. And so once we do some algebra, we get dP over dt equals P times all that stuff. And so then to get pressure by itself, we then take the integral, we move dt over, and we move P over. and take the integral. From here, we get an ln equation with these numbers. As you can see from the line equation, a and b are constants as t changes. So in the ln equation, a is a constant and r is a constant because it's an ideal gas constant, and b is also a constant, and we get the constant c1 because we took an indefinite integral. So then we use the Excel analysis pack 2 tool to generate the three constants, which are C1, C2, and C3. And based on these, we use these constants to solve for A and B. And then we plug those in to get the resulting Leadenheld HFSG equation. And here are the graphs that resulted from this. As you can see, these are even smoother than the ones I showed you before. Not as many wobbles. This is probably the best data, the best results we've gotten by generating our own equation. That is the end of my presentation. Thank y'all for watching.